Let me just check everything else. Okay, that's fine. Fine. Okay, so today we'll be talking about the sensors and Kalman filter. I didn't have as much time to compile a Jupyter notebook today, so we'll go without that. In the next webinar, I'll be using I'll be trying out the C++ Jupyter notebook. Hope everything goes well, and we're showing some additional C++ information that's not covered in the class notes that I think could be helpful. So today, I'll just briefly discuss regarding about sensors and why you might need them, and then we go over this article by Nashade, who I found that, these articles are pretty simple to follow and they're pretty helpful. And the thing is, actually, she took these she took a lot of this information from Udacity, and these are generally the introduction ones, but it's good to have information that remains online. So that's a very I do appreciate somebody putting these up here like this. All right, so in that regard, for sensors, as you know, people, humans, animals, etc., they have a lot more senses than simply vision, right? And this is same thing for vehicles. Self-driving car companies, they use lidar and radar. Some I think uses sonar. I believe Tesla is the one using sonar and images. I could be wrong, but we haven't checked it out. Tesla, let's see, sensors. Sensors for self-driving. Yeah. Okay. That's not what we wanted to look at. By the way, I really do think there was a huge bug in the Model 3 because there was an accident in March, and it's reported that the autopilot was around for 10 seconds and bifurcated the driver. I don't think that's really not. I think that's really uncool. There has to be a bug because like a lot of just lane keeping software and like just crash safe would have kept you from bifurcating for 10 seconds. Let me see, sensors not working. That is not what I meant. And so they use ultrasonic sensors. Okay. I was hoping to get information about sensors, but I wasn't able to find it. That's all right. All right. So back to radar and lidar. Um, so this vision, of course, it's not always going to work out so well at nighttime. It becomes especially challenging during rain, um, and things like that. So, in order for self-driving vehicles to still function well, there are additional sensors such as LiDAR and radar. LiDAR uses a laser, but the laser is not the wavelength is not very long. In other words, it's not very strong. It's usually under 1500 nanometers, and generally they're around 900, as mentioned by Mercedes. And good thing is, the nice thing is they give you a lot of detail. You can get a point cloud from the lidar, and you can detect small objects. You can get a shape of it, objects and things like that. What they are not very good at is seeing long distances. If you are doing highway driving, or going very fast, you will need the radar. Um, and they are prone to things like fog, things like rain, etc., dust particles, things like that. Um, Radar does not have the same problems. However, uh, so radar it can sense long distances. It actually is able to calculate distances without, like, it will directly give you the distances because it's using the Doppler measurements. And what else can it do? So it's not prone to things like rain, fog, and dust. And but yeah, um, that's sums up about sensors. Another disadvantage of a lidar is it's just expensive. So that's why I believe Tesla and certain companies are trying to go without the lidar, just to reduce cost of the vehicles themselves. All right, so let's go on to Kalman filter. So one thing, if you remembered Sebastian's one during the introduction video, that he mentioned that his primary work at Stanford was, or was it? He worked at I believe he worked at Google. Yeah. So his primary work was machine learning, and I'm pretty sure Kalman filters is an applied machine learning technique. So yes, um, and specifically, Kalman filters is applied machine learning technique utilizing the Bayesian inference. I'll get to that later. Um, so this is an article by Nasheed. Um, okay, so sum up what Gaussian is. Gaussian is a continuous function over the space of location underneath the area. So this area sums up to be one, which is one being the probability, right? So this is the full probability, like the probability of all of these sums up to be one. You can think of things over here have very low probability, and things in something in the middle is a has very high probability. And if you have went through the class notes, the Gaussian only have one peak. It doesn't have multiple peaks. So it's characterized by the main, often abbreviated by the mu here, and visible Gaussian, which is the variance or sigma square. So of course, there's more that goes into this, but to think of this task by itself of Kalman filter itself, that's all you really do have to worry about. Passing common phase. So, yep. Okay, so mu and sigma square, best estimate location trying to find, and the idea is you want a very narrow Gaussian because and you'll see why. So this is the exact formula for this equation. More, I think this quadratic function here. Quadratic function below is mu. Then okay, so it's Below x equals mu, then this numerator becomes 0 because 0 is 1. Then it turns out that you have yeah, you do have to normalize the 1 by some square, because otherwise at this point it's not one probability. All right, so what's the variance? Okay. All right, so variance Gaussian spread. Okay, larger variance and shorter Gaussian. Yep. So if you try this out, if you have a larger variance, the center of the Gaussian will be shorter, and that's actually this is the result of this function for any x. What it actually gives you is the probability of that of x, and the shorter your Gaussian is, the shorter your Gaussian is, and the higher your Gaussian is, and that means there is a much higher probability of the main the main here. Think about it like that. And try this out actually. And try anything out like this for a while. So let's go to the Python CLI. By the way, this equation here, this function here, it's also called the PDF, or probability distribution function, by a lot of statisticians. Yeah, and we can try to prove that. Right? Shit, I don't think I need that. Okay. I was thinking about to import. This some coefficient. Minus 5 x minus mu. I wish you had this as text, but and I think that defines the function. Okay. So if we call f of mu, let's say 3, and sigma will be, that's a variance of 1, and what's the probability of 2? That gives the probability of that, which is about a quarter of the time. Okay, so let's look for PDF. So I believe this is sklearn. Nope, that's not what I meant. Function. Hmm. Okay. Don't believe this is instead. Function. Oh, there's this SciPy stats norm. Okay. All right, let's look at this. So SciPy stats, import norm. Um, PDF. Let's see. Let's go to norm and where's the PDF? Uh, okay. So let's see. I'm pretty sure I have this. It's very important. SciPy stats, import norm. Oh, I guess I don't. Well, no module. Install SciPy. SciPy.stats. Whoops. I'm trying to install SciPy. So stats. I'm trying to install SciPy. Install SciPy. Okay, well it does that. Let's move on. So another thing that she brought up is how is the main shift? How do you shift the main, right? Common filter is read measurements and using Bayes rule, which is nothing else but product. Prediction will use probability, which is kind of simple addition. All right, so if you think about it, one thing you do have to think about is that these these um, these main here, they are not in in terms of common filters. These are actually either measured prior, like previous measurements, or current measurements, etc. But here's the thing: you're never certain that these measurements are what is said to be true. So there's always some kind of some level of error or uncertainty, right? And this uncertainty is the essentially the see variance that you have, and that's where you get the variance. And let's think about it. So that you can think of it that way. And now let's go move ahead, right? Here's some prior distribution with all the right Gaussian, right? You have this here, and then when you do a measurement, generally your measurement will be more will be so. What happens here? Um, whenever you do take a whenever you do execute an action, you are not quite sure. Um, you're not quite sure if action executed correctly, if the suppose the robot or your car overshot your the supposed movement, right? That's why it became flat like this. And when you take a measurement, it is more certain, right? Like this. And then when you do an update, right? So when you do an update, you what happened here is that it gets shifted by the main is shifted by shifted more towards the measurement because measurement is more certain, and you'll see why this is by the equation here. So the variance of this guy is the R2, and variance of mu here is sigma squared, right? And we'll see when this happens, the more the weight with the more uncertainty is or variance over here is applied to the measurement. So the measurement gets more weight of the new main as opposed to the old measurement or old main here like that. And remember, these don't have to be like these are not populations. These are not like sample population. I think this is the uncertainty. It's very hard. It's kind of hard to think about like that, but that's essentially Kalman filter is applied like applied statistics or applied machine learning on top of machine learning technique in a motion or motion slash measurement situation. Just think of it like that, right? So that's what happens when you do an update, and the variance is it's updated like so, and okay. So and when this happens, when this happens here, it becomes the variance becomes even smaller, so it's even more certain after this. There's a way to prove it. I don't, I haven't had the time to go through that. Okay. So when you do a Gaussian movement, you do a movement, you essentially, so if you think about adding two mains, it doesn't really make sense, but this is essentially saying the current measurement plus a new measurement. So you're just moving forward. Think of it as moving forward in, in the x direction 10 meters or something like that, right? And this part is this uncertainty. So you become more uncertain because you moved, right? So that's a prediction here, which essentially is just the simple prediction here is just that um, it's going to update, but I'm going to be more uncertain. So think about it like that. Right? So this is this is just everything put together. If you went through Sebastian Strand's the course notes, it's not really. I mean, a lot of people work on that, of course, but um, you will see this example here. So at first, you know, at first the essentially everything is taken from just the measurement because that's you have a lot of uncertainty here, right? The zero is very small; it's almost exactly 5. And then for the next measurement, you can see that you add in more uncertainty, which is uncertainty of like 2, and then you do an update, right? Um, you become less uncertain, and let's see, gets moved towards the yeah. become less uncertain. Okay. Um, update, you become less uncertain, and then you predict, your uncertainty goes back up, update, predict. So this goes in a cycle. Essentially, very soon you will be very certain of your the predicted position, um, etc. Right. See if my thing finish installing. Okay, so that's actually all right. So my SciPy finished installing, and let me see if I can plot the PDF similar to this. PDF of X. Okay. So this will be norm dot PDF. X would be, so the X here would be 2. LOC, I believe, is the main, which is 3. And the scale is 1. Right? And there you go. So this function here is the PDF, right? And PDF is actually I was wrong. It's probability density function, right? All right. Yeah, and actually, I saw another thing about this about the Kalman filter. If you think about it, a lot of land animals, or like humans, or even cats and dogs. If you think about it, when they move, like their their peak goes down, right? When you move, your peak goes down, and you and eventually it goes back up, and you you take another stride, it goes down again. So it's very it's I don't know, it's very it's a probably a coincidence, but very also very I don't know, it's very beautiful thing. So, um, and actually, there's more examples about like Bayesian inference. So um, this article here will go through like a lot more examples. It go from simple probability to the distributions, probability-based distributions, and it will you know it will try to explain to you gradually how PDF is derived, how it works. And I watched a video. I thought this was pretty good. It's not going to give you the formula for the PDF, but it really does give you an intuition of this how this the up prior and prior is derived here. You see like example like this, how it became more certain. This uses a different example. I think you go to example of his his doggo, whose name was what was his name? Rain, Reign of Terror, who seemingly have gained weight, or actually, I wouldn't say weight. They gained weight. The dog, the dogs, like they measured Rain's weight, and it was uncertain. It wasn't like the three measurements didn't add up together to like they were far apart. And by using Bayesian inference, they were able to infer what's most likely the dog's weight. So you can think of this as the same. It's a different application of Bayesian inference, and it's very similar to the Kalman filter example you guys exposed to. I just figure, if we have more examples, it's easier to understand. So I will send you guys. I will send these links through the session Slack, and yeah, I think that will do it for today.